Hello and welcome to Lecture 14. This lecture and the next one on pollution abatement will both be mostly concept. There's not a lot of math to discuss, but this is a bit of history and motivation for the future development of internal combustion engines. As I mentioned in the very first lecture, a lot of the efficiency improvements in the engine have been mostly maxed out, and most of the design efforts today are in making a efficient engine that also does not pollute. So what's our motivation here? Well, the motivation is that air pollution causes more deaths globally than high cholesterol from obesity. So it is a significant contributor to premature death. Um, and if you look at where those deaths are occurring, it's pretty much a population map, with some notable exceptions in the southern United States and other regions of South America that have significantly cleaned up their air and their coal-fired power plants. Um, Okay, so a distribution of where the worst pollution is in the world. You can see some in the Southern California, Western United States, some in the old Rust Belt industrial sector of the United States. You see a lot here in the mountainous Central Asian region as well as the South Asian region. The things that these tend to have in common are a high density of vehicles and tall mountains that cause certain weather effects that trap the pollution. Where there's both this weather inversion that traps the pollution and a lot of people would be major cities like Beijing and Rio de Janeiro are some of the worst air quality regions due to that trapping of pollutants inside the mountains. And that's what happens in Southern California as well. So there's a long history of realizing something's gone wrong with our air and then trying to do something about it. The first and most noticeable one around during the middle of World War II, as the Industrial Revolution was really going at full clip. The cities where that industry was happening suddenly went dark. There was just an immense amount of urban air pollution to where people demanded something had to be done. And something was done, and we'll come back to spend some time talking about what regulations on factories and mainly focus on the vehicles, what was done to combat that air pollution. The 70s was when scientists first discovered that the ozone was being badly damaged up in the stratosphere, the ozone layer that protects us from a lot of the ultraviolet light that would cause skin cancer and other negative effects for life on Earth. And it was mainly found to be the cause of one thing, chlorofluorocarbons, which were used for things like aerosol spray cans, refrigeration, air conditioning, and we adopted some measures rather quickly to address the source of the problems in the stratosphere, and that is slowly repairing itself. It still has a ways to go, but because of the residence time of these chlorofluorocarbons, it was always expected from the beginning to be a 50 to 65-year process, and we're maybe halfway through that time frame now. Acid rain became a big problem, particularly in eastern United States in the 80s, and we began some programs in the United States to really cap down on the sulfur emissions from power plants, and we've made huge strides in recovering a lot of natural ecosystems that were extremely badly damaged by acid rain events. And then most recently, the one that we hear most about now is the global climate change. The alarm was first really sounded in 1992 with evidence that CO2 rising was causing global warming and the host of negative effects attributable to that. We won't spend much on that. Reducing the CO2 is just a more efficient engine or adopting alternative fuels. I'm going to mostly focus on the effects of urban air pollution for automobiles, but I will touch on these other topics briefly. So urban air pollution was first recorded picture of smog. It was 1943 LA. So couple decades after the car first really started taking off, LA is well known for its love of the automobile and was a city essentially designed for automobiles. In 1948, Dr. Hayden Smith was a chemistry professor, and he started identifying that this smog was actually damaging the crops, and him and others looked at what mechanism was triggering it and started to understand what are known as primary and secondary pollutants. So when we say primary and secondary pollutants, the primary pollutants are exactly what would come out of the tailpipe of the automobile. And those can be damaging on their own, depending on what they are. The secondary pollutants, which were first discovered in Southern California, are pollutants that are formed when those primary pollutants react with the air in the presence of sunlight. So the copious sunlight in Southern California was triggering these reactions, so it was turning the nitrous oxide, or NO, into NO2, which is the brown smog layer you see when you fly in and out of LA. And it was also triggering creation of a lot of ozone, which was the eye and respiratory irritant that caused people to cough and shield their eyes when these smog events were happening. So that was the main difference between what was termed LA smog versus the pollutants and urban air pollution that was common in eastern cities and places like London, which was literally just smoke. You could see the smokestack coming from the factories, and the smoke would settle over the cities. That was clearly point source, easy to address. There's the smoke, let's stop the smoke. This urban air pollution of LA smog, completely different mechanism that forms it. It was from a very distributed source because it was primarily from the emissions of the automobiles and required a different set of tools to combat it. The London smog disaster. So this was one of the big events that really triggered folks to make a change with how factories were regulated in terms of what they could emit into the air. The peripheral of London was a industrial town. There were factories running 24 hours a day and spewing all sorts of smoke and high amounts of particulate and sulfur. What happened in London was you had an inversion event. You get strange weather events due to their geography as an island with water being this cold sink. What happened was a large mass of cold air was trapped over the island, over the London area, and normally the ground is warmer than the upper air, and you get a natural convection process that circulates fresh air in. When you have a inversion, the lower altitude air is colder than the upper altitude air. There's no wind, there's no natural movement of the air, and whatever you're polluting just stays close to the ground because it sinks into this cold air. And so over the course of a week, you had a massive buildup of smoke to the point where these pictures, which appear to be in the middle of the night, these are at midday. Midday visibility at Heathrow Airport was about 30 feet. Sun's high in the sky, not a cloudy day. This was smoke and smog that was causing this. Thousands of people died during this week due to respiratory effects of having that much smoke in the air. We're familiar with that here in the England Northwest with the forest fires. This was as bad or worse than that and persisted for quite a while. Other cities around the world at different periods in history as they developed have all experienced this. Delhi had it in the 60s. Beijing experienced it in the 80s and 90s. Mexico City particularly is bad. It is essentially in a bowl in a mountain range at 5 or 6 thousand feet, and experiences these inversion events quite frequently. So as they grew, they're still facing this problem today. They have to be exceptionally clean because of how often those inversion events happen. And that same is true essentially for Santiago, which is right up against the mountains as well. So urban air pollution was relatively straightforward to address. Find the smoke, shut it down. In the case of the automobiles, we're going to come back to that as to what was done to abate the emissions from the automobiles. The next major air quality disaster was the original detection of this hole in the ozone layer over Antarctica. And Professor Sherwood Rowland at UCI discovered the process that led to this ozone depletion, won the Nobel Prize for it. And what was happening were these chlorofluorocarbons, these long chains of chlorine and fluorine and carbon, they were very light, and when they escaped from refrigerators to Freon, when you had hairspray cans, it was what they were using to push that hairspray out of the can, so every time you sprayed one they were released. They would all rise up into the upper atmosphere, and they were quite stable, so they didn't react with anything on their way up into the stratosphere. But once they got there, they became a reaction pathway for ozone to be depleted. So the ozone would actually react with the chlorofluorocarbon and degrade into two different O2 molecules. So a couple of them would get together, so you'd have two O3 molecules and you'd get three O2 molecules. Now ozone down at the ground level is very bad. We don't like it. It irritates our eyes, irritates our lungs. But in the upper atmosphere, it's not going to bother us. We don't spend much time in the stratosphere. But what it's really good at is absorbing certain wavelengths of radiation. So without that block on radiation, the likelihood that we would all have melanomas by now would be much, much higher. So while I'm talking about the fluorocarbons, they were a rather easy fix in some sense. The Montreal Treaty, I believe it was 1978, basically put a ban, moratorium on the use of these chlorofluorocarbons. And the reason why I say it was relatively easy was that at the time there were only 2 or 3 major companies in the world that produced these. Your 3Ms and DuPont. They had made this manufactured. It was a man-made molecule that didn't exist in any real significant amounts in nature. They saw this regulation coming. They had alternatives to the chlorofluorocarbons. Now, in terms of why we use the chlorofluorocarbons, they were very good as a refrigerant because when you drop the pressure on a chlorofluorocarbon, they drop in temperature a lot due to their molecular shape. So that is what makes them a very good refrigerant. When we replaced the chlorofluorocarbons with other things, ammonia is one example, the refrigeration, your air conditioning got less efficient. Eventually we've been able to make up for that with more efficient compressors and more efficient heat exchangers, but at the time there was a sudden drop off in efficiency of refrigeration systems. But the 3 companies or so behind chlorofluorocarbons had alternatives ready, and to them it was a business opportunity that they had sold everyone equipment based on chlorofluorocarbons. They had sold tons of chlorofluorocarbons, and now they got to sell you a replacement. They got to make the same sale twice. They didn't really balk too much at this regulation, and the science was very clear and very well explained. All of the countries got together and signed the Montreal Treaty, and it has for a long time been the gold standard in these international air quality type treaties. Um, so this is again just illustrating what happened to those chlorofluorocarbons that would make it all the way up into the stratosphere. Most of the other emissions we're worried about, your soots, your unburned hydrocarbons, they don't generally make it past the cloud base. So all of our weather is down in the troposphere. Um, so any other emissions tend to get trapped in those winds and recirculated. They come down as acid rain, or they just float in this region of our troposphere. Um, but it was the chlorofluorocarbons that were generally inert enough that they could pass right through that area and continue to rise all the way to the stratosphere. So speaking of pollutants that would rise up into our weather and come right back down, in the 1980s, we started to see entire forests in the Northeast start to die off. And it was particularly acute up in the Adirondacks. Entire ecosystems were beginning to shut down due to the acid rain. And it's been quite a recovery story for a lot of the natural spaces in the Northeast since the 1980s, and we put very strong regulations on the emissions of NOx and SOx from power plants. So the Northeast was heavily dependent on coal, and a particular type of brown coal that contained a lot of sulfur. There were, not generally filtering or catalyzing processes in the smokestacks. They were smokestacks, and the smoke rose right up and came back down as acid rain. Nowadays, when we see smokestacks, what we're familiar with is the white plumes, and that's generally steam. What you see on campus in the winter when our steam plant is running, it's not smoke, it's steam, dissipates very quickly. But at the time in the 80s, these were actual smokestacks producing smoke. In the 90s then is when we first started really banging on the drum that our emissions of CO2 were causing changes at a global scale. And while the science of this gets muddled in political rhetoric, the basic energy balance is really straightforward and simple and quite indisputable. If you have a molecule that absorbs a specific wavelength of sunlight, being more in the infrared region, you're generally going to trap more heat. The way that occurs is the incoming sunlight has something close to a black body distribution of radiation at 5800 degrees Kelvin. And so that's mostly in the visible and ultraviolet, near visible spectrum of energy is where the light is coming in. Some of that's absorbed by different molecules, mostly water in our atmosphere, but then some amount hits the Earth. And generally there's reflection accounts for some of it, but the majority of the energy leaving the Earth is re-radiation. And because the Earth is not at 5800 degrees Kelvin, it emits radiation with a black body spectrum closer to 300 degrees Kelvin, which is definitely in the infrared region of wavelengths. And CO2 is a strong absorber of infrared wavelengths. So CO2 in our atmosphere allows the incoming sunlight to continue to pass in, so we have the same amount of energy coming into the Earth, and then the CO2 traps the infrared light leaving, thus trapping some of the heat from leaving. Simple energy balance dictates that the energy on the planet would rise. Now, is this attributable to human? At this point, the consensus scientifically is yes. And those that don't accept the scientific facts sometimes still accept that global warming is happening, but refuse to accept that it is human caused. There's a number of trends, not just air quality and CO2, that are undergoing what's being termed as the Great Acceleration. When you look at information travel, human movement, a number of things all going under this Great Acceleration. Well, this is happening in carbon dioxide, nitrous oxide, methane, sulfate, and it's this great acceleration of our impact on the planet that is causing this. So the IPCC report, if you hear this thrown around, this is the International Panel on Climate Change, releases a study every 4 to 5 years, and they put together and package the hundreds and thousands of scientific studies around the world to form what the consensus projection is for the planet. You can see the temperature anomaly before 1980 fluctuates mildly, plus or minus 0.2 of a degree, and since then we have skyrocketed upwards. And the projections only make it look worse. Even doing just about everything we can to combat it, it's still going to rise significantly over the next several decades. So taking a step back, now that we've identified what the problems are, what was done about it here in the United States? In 1947, California, after the LA smog had become unbearable, was the first to pass an Air Pollution Control Act. And that led to the Air Resources Board, and specifically the South Coast AQMD, Air Quality Management District, which has been a pioneer in regulating emissions for the last 70 years, and they continue to do so. The air pollution controls were expanded nationally in the 50s by Truman, but were not codified into federal law until the 63. There was an amendment in 67 which greatly strengthened the Clean Air Act, set up air management districts all throughout the country where air quality was deteriorating. In 65 was the Motor Vehicle Air Pollution Control Act, which had the most direct effect on automotive manufacturers, and a number of the manufacturers took different ways to address this. Eventually consensus pulled around the catalytic converter, and we'll talk about that in the next lecture. The 1970 Clean Air Act it formed the EPA and identified specifically these criteria pollutants, as they are termed, those being ozone, sulfur dioxide, nitrous dioxide, carbon monoxide, particulate matter, and lead. Eventually, they'd initially specified the total hydrocarbon emissions as one of the criteria pollutants that was dropped at the time, but now regulations for the unburned hydrocarbon emissions do exist. In 1970 was also when lead was banned as a fuel additive. So if you wonder why the gasoline always says unleaded gasoline, where we don't use leaded gasoline anymore, this is a remnant of the 70s when there was both lead and unleaded gasoline. In 1990, they really started to focus on the emissions, particularly the unburned hydrocarbon emissions from the vehicles, and identified 118 different chemicals that were in those unburned hydrocarbons, and started to see if they could improve that. In 1997, we started to classify particulate matter into different size categories because it has different impacts on human health, and we'll spend some time on that later in this lecture. In 2007, fairly landmark case in the Supreme Court, it did rule that the EPA has authority to regulate carbon dioxide emissions. Specifically from automobiles and other vehicles. They did not expand that to carbon emissions in general, and that is where things get a little bit gray. So those original, those criteria pollutants that we focus on, what are they? Well, particulate matter, we'll start with that one. PM10 and PM2.5 are the ones that are regulated now. There are new pushes to regulate what is known as ultrafine or PM.1. But particulate matter is what we would think of as smoke. Clumps of carbon that have burned together, ash, but very, very small. 10 refers to 10 microns in diameter. So PM10 is less than 10 microns, and that is generally small enough that it's going to make it past your natural filters. It's going to make it past the mucus in your nose, it's going to make it past your esophagus, and it will actually make it into your lungs. Larger particulate, smoke, soot, that generally, yeah, it'll irritate you, it'll clog up your nose, but it ironically is not as bad for your health as the smaller particulate that you generally can't see. PM2.5 is even smaller particulate, less than 2.5 microns across, and that size difference is critical. So something up to 10 microns can make it into your lungs, but if it's even smaller, it can actually cross the cell walls from your lungs into your bloodstream. Now it's mixing around in your body, and what was in that soot isn't just pure carbon, it's carbon plus all sorts of carcinogens that are clearly cancer causing. The PM, the ultrafines now that we're considered with 0.1, they don't even have to be inhaled. They are so fine, they can enter your body even through your skin. You still, breathing does circulate a lot of them, and that is how the majority would enter your body. Once they're in there, they basically have free reign and can pass through cell walls and just wreak havoc. Carbon monoxide is another one of these regulated pollutants. It is colorless, odorless, so you're not going to see and detect it, but it will kill you. What is in our blood that transports oxygen around our bodies, it is far more likely to bond to a carbon monoxide molecule than an oxygen molecule. So if you inhale carbon monoxide, even in very low concentrations, it greatly diminishes your ability to send oxygen throughout your body, which we obviously need. This is why we have carbon monoxide detectors in all of our houses, and very low amounts will kill us. Parking your car in the garage and leaving it running while you're sitting there, that type of suicide is poisoning yourself with carbon monoxide. Basically, you cannot breathe, or even though you breathe, your body isn't able to recover any oxygen. Sulfur dioxide is a criteria pollutant, less for its direct impact on human health and more for its impact on crops and natural spaces. Sulfur dioxide is what leads to acid rain, and the acid burns through leaves and turns lakes acidic such that it kills the organisms living in that lake. Nitrogen dioxide is a brown gas that gives smog its color. It's actually the emission of nitrous oxide reacting with oxygen in the air that often forms the majority of the nitrogen dioxide that forms smog. And ironically, I think it's the fact that this gas is brown that really irritates people. It's not a particular health hazard in the way ozone or carbon monoxide is, or SOx, but it's not very pleasant to look at. If it were perhaps prettier, it might not even be a regulated emission. We might construct nitrogen dioxide generators if it were a prettier color. Who knows? Ground level ozone is, as I've mentioned, an eye and respiratory irritant. It is often a secondary pollutant when the nitrogen, the NO, is emitted from the tailpipe and it combines with an O2 molecule. You create NO2 and a free oxygen. If that oxygen then combines with another O2 molecule, we get ozone formed in the lower atmosphere where we don't want it. Ozone in the upper atmosphere, great. Ozone down here at ground level, not good. We've talked about primary and greenhouse gases. So regulations, what are they? Well, the way they're measured is either on a part per million basis or on a weight basis per unit volume of air. And oftentimes they are regulated both on a short-term event such as 1 hour and a longer-term average, 8 hours or 24 hours. So let's take a look at carbon monoxide. We've decided that for a 1 hour, maybe in the peak of the day, rush hour traffic, up to 35 parts per million would be tolerable, but as an average throughout the daytime, we'd like to keep that below 9 parts per million. Generally, the places that exceed that are exactly what you think of: Southern California, as well as what's known as the inland valley here, that has a lot of agriculture that stirs up dust, and they mainly violate these standards in terms of particulate, whereas the LA area generally violates ozone and NOx. So the regulatory agencies that oversee this at a federal level, you have the EPA. It sets national air quality standards. California has stricter standards as they've been facing this for longer. So California has the Air Resources Board that covers the entire state, and the South Coast Air Quality Management District, which is a legacy as it existed prior to both the California Air Resources Board and the EPA. And the South Coast AQMD has the strictest regulations in the country. So the most common regulations that have been put on vehicles are, one thing is known as the CAFE fuel economy standards, and it is a steady decline in the emission, well, it promoted more efficient vehicles over a number of years. So if you have a larger vehicle, you're allowed to get lower MPGs, but as time progressed, we needed to raise the average miles per gallon standard. And so where we are 2017, we're most of the way from where we were when the CAFE standards went into effect in 2012. We're rising up to this average vehicle fuel economy standard of 50 mpgs. And that is the target most manufacturers have been trying to get their fleets to. And so when I say a fleet, that means GM makes trucks, they make cars, they make vans. Some of those will never achieve 50 mpgs, some already do, but their fleet average, so the average of their new cars sold, will have to reach 50 mpg. So a lot of the smaller sedans that already do this are essentially subsidized every time someone buys a giant truck, just because they're mandated to meet these standards. And the way it's broken down for the criteria pollutants is there's different standards based on the size of the vehicle. So these bins refer to different vehicle classes. So your bin 1 and 2 might be the very small two-seater coupes. You get up into the bin 6, 7, 8. This is when you're getting into light duty trucks, typical consumer trucks, and then the bins 9, 10, and 11 are your heavy duty large work trucks. Generally, everything is based on grams per mile of these pollutants, so they put the cars on a dynamometer and they basically trap the exhaust in a bag. They capture all of the exhaust in this sort of like a vacuum bag that collects all of the emissions, and then they put it through a analysis system that measures the weight of each of these pollutants. And generally, these criteria pollutant standards have been ratcheting down at a pretty steady clip. And what that results in is quite a bit of success since they've been put into effect, despite a continuous increase in the number of vehicles on the road. So when the control technologies first went into effect in the 50s, there were projections as to what would happen in terms of hydrocarbon, CO, and NOx emissions. And because of the control effects, we've actually decreased the emissions of these pollutants significantly. But there have been some setbacks. So a lot of the first control strategies to reduce hydrocarbon and carbon monoxide emissions was to have more complete combustion. So we ran the engines closer to stoichiometric, and what that resulted in was actually more NOx production because the flame temperature in our engines was higher. We've since developed in the 70s is when the catalytic converters came on the scene, and that is what allowed us to reduce the NOx. So this chart is showing on a bigger scale what was the impact of those regulations in one of the most polluted areas of the country, the South Coast Air Basin. So these are the number of days of the year which exceeded those thresholds set by the EPA. So in the 70s, basically 2 out of 3 days of the year, almost every day from March to September, was exceeding the standards. So the summers down there, despite the wonderful sunny weather, were not pleasant. Since then, in the 2000s, it's about 1 in 10 or 1 in 15 days now that would exceed the standards for ozone. PM 10 and 2.5, we talked about those extensively at this point. The sources are basically anything that is burning a fuel in a non-premixed type combustion forms lots of this soot. Soot being heavier than 10, but then this fine soot, PM10, and the even smaller PM2.5 have finally been controlled. We can do that with scrubbers, filters, and even these things called electrostatic precipitators. SOx, SO2, also emitted from mostly power plant and refinery, things that were working with heavy chemicals that had sulfur in it. Your gasoline fuels are fairly low sulfur, but diesel engines did have a significant amount of sulfur, still do, and that is why we use diesel exhaust cleanup, basically urea that is cleaning up the SOx in diesel combustion. Carbon monoxide, talked about that as well. It's primarily a source of incomplete combustion. So the first step to fixing this was basically making sure we had better, more complete combustion in our engines. Part of that was increasing the flame speed so that combustion could complete before the piston started moving. A lot of the improvement was made in industrial boilers, which burn a lot of fuel in this country to heat things in the winter. And more efficient boilers, water boilers in your home, all of those have reduced CO emissions. Lead was originally the primary sources were smelters, the manufacturing of batteries, garbage that contained lead would seep out into water. Leaded gasoline was emitting lead all over the country into the air. We've basically phased lead out of gasoline, and all of these individual point sources, smelters, and lead acid batteries have installed pollution equipment to really reduce lead leakage into the natural environment. Stratospheric ozone, I spoke about this at length earlier. So this is when oxygen plus ultraviolet light splits that oxygen molecule in half, and then each of those individual oxygen atoms go and bond with another oxygen molecule and form ozone. And this is generally a good thing in the stratosphere. Prevents skin cancer and prevents crops from dying from the additional ultraviolet light. When the hole in the ozone formed, one of the things they were detecting was a significant decrease in phytoplankton in the ocean. So those are things that really help us breathe because they produce oxygen, and as well as doing atmospheric measurements, they were able to detect this ozone hole and quickly banned the chlorofluorocarbons. One interesting fact here is because CFCs can last 50 to 100 years, and that's what I mean, we're halfway through this phase, so over the next 40 to 50 years, we expect the ozone hole to close down and shrink. But because of their long residence life up there, one molecule, one chlorofluorocarbon, can actually break down 100,000 ozone molecules. So that is why even a small amount of these emissions had a very, very big impact on our atmosphere. Ground level ozone is something we like. It's formed with a slightly different process. It's generally nitrous oxide being emitted from our vehicles, and that reacts with some organic compounds to form NO2, which is the brown smog. That NO2 can break down to have a free radical oxygen. That free radical oxygen can, just like in the upper atmosphere, combine with an oxygen molecule to form ozone. And this cycle here is set up, these four equations, sort of a step 1, step 2, step 3, and then back to the beginning, because it regenerates the original ingredients while it produced ozone in the process of these four reactions happening. Okay, nitrous oxides. The source is primarily vehicle combustion and industrial sources. What we do in terms of jet engines or power plants is RQL combustion. So we burn very rich first, so it has a low adiabatic flame temperature, and then we dump in a bunch of air and burn lean, and then it's also a low flame temperature, and that prevents NOx from forming. The type of nitrogen oxides that exist, NO is colorless and odorless. That's the primary pollutant. The secondary pollutant that forms from nitric oxide is nitrogen dioxide, and that's the brown smog molecule. There's some small amount of N2O that forms. This is laughing gas, and certain power plants, depending on the technology, particularly contribute a lot of N2O into the atmosphere. Soot. Soot sounds bad. It's actually helpful in terms of what we're trying, the primary function of a boiler or a furnace, which is a fireplace, is you want heat. So this is why a wood fireplace often feels different than a natural gas fireplace in terms of heating. So the natural gas fireplace will still heat the air, and then you need to somehow direct that air into the room to heat the room. the old classic wood burning fireplace radiates the heat because there is a lot of soot formation in these clumps of carbon that are red hot. The ash that glows is what's radiating the heat out at you. So more surface area, more radiation. So it's better for heating, but it is bad for our health in the atmosphere. They're generally quasi-spherical particles. They have somewhere in the vicinity of 1,000,000 atoms in one of these soot particles, and they can be mostly carbon with a little bit of hydrogen just buried in there. So little hydrogen that it's not really a fuel anymore, but it is not pure carbon. So what does it look like? Here's some example images of what a individual soot particle might look like. Zooming in even farther, each one of these specks here looks like a sheet of carbon atoms in these rings. When we look at a flame, when we see the yellow flame of a candle, what we're seeing is the emissions of these soot particles. So when we shine a laser through that would highlight where the soot is, the soot in the air lines up exactly with that flame we see. So again, in a non-premixed flame, the heat you're getting, that you're seeing, is the radiation from the soot particles. You're not actually seeing the combustion reaction, you're seeing radiating soot. Health impacts, I think I've covered this, that the large particles get trapped in your nose and esophagus. It's the small particles that are less than 10 microns that really get into your lungs and have long-term health impacts. Volatile organic compounds, this is a catch-all name for basically everything else. Organic compounds means there's some amount of carbon in the molecule, but it is all sorts of nasty stuff that is mostly carcinogenic, and generally bad for our health. So this is the catch-all for essentially everything else that isn't a nitrous oxide, a sulfur oxide, or carbon monoxide. So everything else that's got hydrogen, carbon, all sorts of nasty stuff falls into this category. You can break it into smaller categories of aliphatic, aldehydes, aromatics, basically all the ingredients of our common fuels, and then some other nastier stuff like formaldehyde that forms. So long-term effects have been studied by a number of people. So the LA Basin, there was a 10-year study basically demonstrated that the smog had a aging-like effect on lung function. Folks that were 40 years old had the lungs of a 55-year-old. 12-year study in the Netherlands focused on SO2 and PM, demonstrated similar negative chronic effects. In rural Pennsylvania, there was a long study that identified respiratory symptoms from the acid rain. The most famous one is this Harvard 6 cities study, where they basically correlated 6 major cities' air quality to the rate of premature deaths in from certain health effects. And the correlation between the air quality and the long-term average air quality and the number of deaths really convinced folks that it was the air that was killing people. In terms of scope in some of these polluted cities, so smoking clearly is going to cause lung cancer, and smoking at its peak was causing about 100,000 new cases of cancer associated with smoking. At the same time, the air quality is a couple order of magnitude smaller, about 2,000 people per year developing cancer that could be directly attributable to emissions from vehicles and other combustion technologies. So smaller but not insignificant. And that'll wrap up this lecture, and we'll have one more on pollution abatement technologies.